Thank you, everybody, for taking time out of your busy day to join us again here at the JETSON AI Lab. Today is July 9th, and in the past couple of weeks, there's been a lot of vision model releases actually that are quite exciting to dive into. On one hand, the Open VLA embodied robotic model for manipulators came out. Florence 2 came out from CVPR. And maybe it's because there's been some image processing and computer vision conferences recently. But we're going to dive into those, cover some enhancements that we have in the new containers things coming out, and also next steps that have been taken with on-device fine-tuning, and that continues to progress, and we'll discuss those workflows and what it all means. So with that, I'll start sharing my screen here. Let's go. Can you guys see this?
Yeah.
All right, very good. Okay, so this Open VLA model came out, I think it was like 2 or 3 weeks ago. And this is, I think, the first or one of the first foundational embodied agent models that's open weights. There's been this OpenX embodiment data set out for, I think, a year or so now, which is very large and like a consortium of other data sets that have been collected with manipulators, mostly with teleoperation. There's some synthetic data in there, but then a large collaboration of different universities and researchers went off and trained this Open VLA, which is very much like a vision language model, except that it outputs control tokens instead of words. So it takes in an image, it has a vision encoder, in this case, a dual vision encoder, and then it outputs 7 tokens because the control space has 7 degrees of freedom for these robot manipulators that it's trained on, and it discretizes the control space into, in this case, it can be represented by 256 different tokens per control variable. So it's 8-bit control resolution on it. And otherwise, it's quite similar to a VLM in concept. We can delve into some of the differences they found in practice with it. But as I mentioned, it uses Dino V2 and SIGLIP vision encoders, and then just goes through a Llama 2 7B that they fine-tuned. And then there's a bunch of detokenization and normalization stuff on the end. And all the weights are open, and the code to run it, it uses, it's built on this prismatic VLM training data set, which is pretty nice and has all of the code right in here for it. So the past week or two, I've been going through and porting all of this and getting it all quantized and optimized down, and got some initial results out of that here through the same nano LLM, nano VLM pipeline that we use to run the live Lava and live Vela. So the FP16 implementation is just this one through Hugging Face, which runs at approximately 1.1 frames per second on AGX O-ring. But then once we start applying the quantization using MLC or AWQ, just like we have been using in our other agents for better real-time performance, we can see we get multiple times speed up out of that with an error rate of under 10% of all of the quantizations. So basically what I did to evaluate this was just run the original model alongside this quantized one and evaluate it on this Droid data set here that you can see all these different scenarios that it has. And I'd just compared the control outputs of it and made sure that they were close and reported the error here. So it is interesting. You can see the fastest one is also has the most error, but even so, 7.2% is well within the realm of not much degradation. But I did approach this one with more rigor than just like the image captioning VLM, because you want this one to actually be like controlling stuff and require more precision. So even at the slower one, FP8 is still quite accurate in terms of any error that it accounts. And with respect to the frames per second, in the paper here, the original paper, it says that, let me see if I can find where it says this, but for their tests, here it is, they used an A5000 discrete GPU and were able to run that up to 3 hertz with 4-bit quantization. So with our extra optimizations, we're essentially able to replicate their real-time level of performance that they got with smooth control, but on JETSON, as opposed to like a beefy A5000 GPU. So this could like feasibly actually be deployed on a mobile manipulator or other like industrial environment that would want to use a portable edge device like JETSON. And I believe at int 8, they were only able to run at 1.2 hertz. So this like level of somehow we're able to get the same performance out of JETSON as they were on, a much more powerful and compute, resource of GPU, was because of all these like extra optimizations and APIs that we put into it and go the extra mile there, as opposed to like just running it through the upstream Hugging Face implementation of it. So there is a lot of really interesting details about this in the paper, things like why they ended up with the architecture that they did. In particular, the vision encoder, the way they did those is a little bit different than the VLMs, which would those VLMs are trending to using higher res vision encoders like SIGLIP at 448 resolution or whatnot, whereas these use smaller ones that are stacked because they said at higher resolutions they did not get performance or accuracy increase, but they did get accuracy increase by combining Dino with SIGLIP. And the reason that they think that is because Dino has more spatial awareness and context to it, which is a common issue that people encounter with the VLMs, is that they're not very good spatially, or like accounting objects or things like that. And these guys like combined a bunch of different vision encoders and fine-tuned them, and were able to get that performance. So it is a interesting challenge with like the differences that this has. There's some other things about it that I just noticed initially, and I'm going through now to like actually run this on the data and get it in simulator, and we'll like deploy it on real robot arm. And I think will be a good entry point for people to like actually start applying these vision language models to like real robotic applications. But another thing is it uses all like the external camera right now. It doesn't, a lot of these data sets have an onboard camera on the wrist of the robot that gives like the first person perspective, but this uses all like the third person cell view of like the workspace, which is like fine for a lot of typical applications of a robotic arm where it's like installed in a fixed location. But I think OpenVLA is a great entry point for these models, and hope that they continue to train and enhance those. So it was good that we proved that this is like feasible to do, and with the whole fine-tuning workflows that we'll discuss later in this meeting, we should be able to set up like an interactive teleoperation and data collection workflow with ROS, and like do the training and be able to deploy it seamlessly which is kind of what these guys have done now. Most of this data, it was just collected via teleoperation and then like aggregated into terabytes of data that they then trained it on. But it does say in the GitHub for this repo that it's like pretty much assumed to deploy it on a real robot, it will require fine tuning for it. Where does it say this at? It says somewhere it's like it doesn't really excel at zero shot, and you will most likely need to fine tune it unless you're very closely replicating one of the robotic arms that they already have it set up for, which is understandable. But it does require that like extra step to try this all out, which is where we will enter sim to real and leverage like Isaac Sim and stuff like that. So next, my next thing to try with this is to, after getting it running on like some of that real-time video data, like from here, just to like test it and show the output, kind of like we've seen with the video lava, is to get it in Isaac Sim, and we have some environments like this that should be real easy to test this with. And Nigel, I think you said you're start looking at similar thing too with Isaac Gym or another similar tool to that. And there's some other ones in here too that we should be able to do. I just want to like test this in real simple environment and use JETSON with hardware in the loop to profile that like 3 hertz is enough for smooth motion. I'm assuming it is because the author said that that's what they use, but just to like understand those performance implications and to see if this is feasible to do in practice. But if it is, I think it will be a great tool because you can just command these with natural language. Like if you go into this data set explorer, you can see what the person told the robot to do in here, and it just like follows that natural language prompt that you give it, which is really like the whole point to all of this, is be able to speak to the robot and it just intelligently goes off and do it without you needing to manually code all of these different modes or state graphs or all of that stuff. And this might just be the beginning, much like we saw with VLMs and Llama and stuff like that. But it's a really good entry point that I feel. Eventually, want to get this on like actual real robot, and I have one of these from, this is like 8 years old now, and never built this around JETSON TX2, but have since then always been working on like the brain and the computer vision part. But I feel like we're finally getting to a point where we like got all these pieces together where you can just very intuitively, simply collect data and fine tune these models to go out and do autonomous navigation and manipulation, things like that. Hopefully without needing to code a whole lot of other stuff in there too. I think there'll always be like safety layers and things like that you'll want in there. Someone from the group had also forwarded this to me because I was looking at the OpenVLA is all trained for manipulators, which is a complex problem to solve. And, you know, the high dimensional 7 degree of freedom control space. And obviously they need these like large models to solve those challenging like gripping and picking. All of those manipulation problems are quite difficult. But I was wondering, like, what about UGVs or like ground robots? Is there something like that for autonomous driving, essentially? And it turns out that there is, from some of the same authors of OpenVLA, and this is just using VITs to do different smart navigation tasks based on like intuitive landmark recognition, and you're able to add waypoints into this scene graph that is pretty simple to work with. And they actually built this on JETSON over Nano as well, which makes a lot of sense. So this is just like a few different VITs that basically take in images, output paths, or other factors about like your navigation tasks, and it will automatically be inclined to go out and like explore areas it hasn't seen, automatically like evade obstacles or stop for people, other things. So these are very interesting models as well, and do not seem to require such high-end computation that you might see from like the full-on open VLA that's 7 billion plus parameter model. So it could be really exciting, like combining all of these together, and then you get a mobile robot with manipulator on it that you can just control with your voice and have intuitive mapping of your environment and stuff like that. So it could be an exciting way to apply all these latest advances in Gen AI to robotics, and we'll prove out those workflows, and all of the stuff that's happening with on-device fine-tuning, I think plays into this really nicely as well. So I think they have a third model here too that I still have to study, like how these all work together and mesh, but they do have a implementation of all this running in, this is in ROS Melodic still that they have it in, but it does run on the Ora Nano, so performance-wise, it's fine. I'll have to take a look at probably porting this to Humble and ROS 2 and using other stuff from Isaac ROS to further increase the performance. But all in all, it does look exciting that these new foundational models for robots are coming out. Dave Ross one for life. It's interesting, on the forums recently, there have been people asking, like, how do I get Noetic on Jetpack 6? And I'm not sure that we ever really found out a good way to do it, because I could not build it under 22.04 anymore. But if you don't need CUDA in it, then like you're okay. You might have to get creative if you do need that, which admittedly is kind of the point. Okay, so bunch of different activity going on in like the vision space. There was also this Florence 2 model that came out from Microsoft at CVPR, which I'm going to let Nigel talk about because he's been working on this, but this has some very interesting vision capabilities as well, and is a smaller, less than 1 billion parameter model that we should look at leveraging. Okay, I will turn it over to you now, Nigel.
Sweet. Give me 1 sec to just share my screen. Oh, let me actually make sure I have audio.
Sure, yeah.
All right. Are we all good?
Yep, we can see it. Thank you.
Cool. All right. First of all, hey everyone, I'm Nigel Nelson. I'm a machine learning engineer with the HoloScan team here at NVIDIA. Been attending these meetings for a while, but pretty excited to finally be talking in one. So before I go too much into the details, I think the demo is pretty fun here. So what this demo is Florence 2 running on one of my team's repos called HoloHub. We'll get into all of that because I'm sure that many, if not most likely all of you, are unfamiliar with HoloHub and HoloScan. So we'll get there, but for now, let's just check out Florence 2 and all of its fun vision tasks that it can do. So we have object detection, captioning, detailed captions. It's kind of it's a vision language model, but it kind of does it all. It's very, very cool. And as Dusty alluded to, it's sub 1 billion parameters. So this model that I'm running in this video here is the 700 million parameter model, but they also have a 230. But it does pixel level annotations, so segmentation there, and promptable. So you can tell it exactly what you want to segment and it comes up with it. And also OCR. So let me pull up the paper on this model.
Yeah, obviously all these different vision tasks that it can do are probably the most interesting thing about this model. And in addition to it be a mini size, how do you actually interface with that? Or like when you're changing the dropdown, is that a different function in the Transformers API that you call, or is it just a different text prompt that you send it, or I
Yeah,
haven't dug
so
into the code.
so it's a little different than like, because my whole experience is in decoder only large language models and like the more traditional VLMs where we have a encoder, like a clip, and then
Yes.
multi-layer perceptron into kind of like a text embedding space. And then you just have the model kind of learn how to work with that.
Yeah. And I thought
But
this is a sequence to sequence, like BERT.
exactly, yeah. So that's what's going on there with the drop-down menu, is it's each one of those is a different task that it's trained on. And so you feed it a task prompt, which kind of tells it which sequence to sequence task it's doing from its training. And then also, depending on what you're doing, as far as the actual task, then you can feed in an optional prompt. So here's the architecture of, they use an image encoder, which is dual attention VIT. And then those embeddings are concatenated with your text and optional location embeddings. And that is fed directly into encoders, into decoders. So really interesting architecture, to be completely honest. Not an expert on the encoder decoder architectures,
Yeah.
still getting comfortable with this model. But
Well, in like 2019, when before the causal LM decode only architecture really took off, the sequence to sequence was what most people were using, and even at the time, BERT was pretty amazing for NLP stuff. And while this will not, like, we were going back and forth. I like, this is not in llama.c++ or other LLM APIs like that, because it's not similar at all to those autoregressive decoder only ones. But I think we should be, like, years ago I had accelerated BERT with TensorRT just through like Onyx, and should be able to accelerate with that. We can get into performance discussion later about this.
Yeah, I would love to see that happen, because this the implementation that I had it's just using the one library out there that supports it right now, which is just transformers natively. So this is running on a DGPU. So this is an A6000 at FP16, and again the 700 million parameter model. And in this video, I try to include this little bouncy ball. It's a little screensaver, so you can get some sort of a feeling for the kind of latency of the model. But again, like, the interesting part of this model is, while it's doing all of these vision tasks, where normally for a bounding box model segmentation, you're outputting the pixels, but this only outputs text. So it is outputting kind of a JSON spec with the bounding box coordinates. And then for the segmentation, it's literally outputting each one of the edge points going around the entire segmentation.
That's
So
nifty, as opposed to the
yeah,
mask.
it's really really interesting. And
Yeah.
the latency kind of works just like a vision language model, as far as the complete latency for it to complete generating, where, the shorter task, like the quick caption, doesn't take much time at all, because it's, a couple dozen tokens. But then you can see in this video, I swap out of the segmentation fairly quickly. And that's because it takes a while, because like I said, it's outputting each one of those points that goes around it. So in some of my testing, if you give it a more complex shape, like, I don't know, in this picture, say that I was just to do the Wi-Fi router, because there's all of those little edges that it has to work around, that will take it much more time. Like, I tried to segment myself, and, it froze there for like 15, 20 seconds until I could get each one of those points. But it is.
Yeah,
Go ahead.
like, have you dug into the code of, I guess it is outputting more tokens in that mode, and it's a longer JSON output that, and like, I know we wanted to talk about like grammars and stuff too, but does it do anything to enforce that, or is it just naturally trained to, like, oh, in segmentation mode, I output this JSON schema?
Yeah. again, this is where my knowledge gets fuzzy. I want to understand it more because it does output it like 100% consistently. And coming from
Yeah,
like a decoder only experience, I don't intuitively understand how it's able to just every single time not hallucinate some incorrect spec. It
yeah,
consistently outputs perfect segmentation masks and bounding boxes. And yeah, it's a remarkable little model. Like I'm really, really impressed at the just zero shot capability out of the box. Like as soon as I got it working and turned it on, and I would tell it to do the Wi-Fi router, check segment my watch, it can pick up on them immediately. And it's interesting. There's like a little bit of prompt engineering in this, where when you go to the beginning, just let it kind of output what it wants as far as object detection. You see here, like it doesn't pick up on my headphones, or actually it thinks that it's actually a computer mouse there, but doesn't pick up on the watch, doesn't pick up on the Wi-Fi router. But then when you actually prompt it and say, segment the watch, segment the Wi-Fi router, it does pick up on it. So
interesting.
it's
Yeah,
really, it's a really, really fun little model to check out.
yeah. I'm just browsing through the Hugging Face code here for it a little bit in the background, and we'll have to dig more into this for like all the different modes it supports. And it looks like it uses a David dual attention vision transformer,
Yeah.
and then BERT text encodings, and then this encode decode architecture. And so, Nigel, do you also know, do they have fine tuning scripts for this available? Like if
Yeah.
you wanted to add some other
Yeah.
mode or
Yep.
okay,
Yep, and
okay,
that's the beautiful thing why I'm excited about this model is they released at MIT. So
okay.
you
All
can
right.
kind of do whatever you want with this thing, which is awesome.
Yeah. That is very interesting to just kind of make this meta model that can do a bunch of different
Hmm.
kind of related tasks and leverage that like foundational training
Yeah.
that you put into it. But it doesn't need switchable LARAs or other things like we had kind of discussed. Yeah. Hey, Mike from Ridgerun, you got a question?
Yeah, actually, a comment for those interested. The author just uploaded a video to YouTube on how to fine-tune Florence. So pretty exciting.
Okay.
Yep.
Yes. All right. I will after I work on the OpenVLA a little more, I will switch gears to this and see what kind of optimizations that we can do, because it would appear to run it like much like the VLM, like you said, Nigel, it's variable frame rate, but it would seem to be
Mhm.
about like 1 to 2 FPS on,
Yeah.
I think like an A6000 you're running this on.
Yep.
So ideally we could get it up to, I mean, NanoAl runs at 30 FPS on OREN.
Mhm.
And how do you feel this compares to like the dedicated VITs for detection and segmentation like SAM and HAL VIT?
Again, completely like qualitative and just
Yeah, yeah.
my own anecdote, it feels on par. Like,
Wow. Okay.
and
Sure.
that's the amazing part is that it's promptable. Like the what I've used before for kind of specific segmentations like this where you can like output, segment the chair, is people will use the segment anything model in conjunction with grounding dyno, where you prompt grounding dyno
Yes.
and then based on the output bounding box, then you find the segmentation from SAM with the most overlap. But this is just so cool
Yeah.
that in
It-
one shot,
yeah.
it just does it.
There were some cool Hackster projects that were doing that on JETSON, and combine literally just like you said.
Mhm.
And but this does raise the point of, is these like multiple model agent prompt engineering stuff we're doing really just a band-aid for not fine-tuning stuff into a larger or more capable model? And in this case, they kind of just like bundled it all in.
Yeah.
Could you walk us through some of the other lesser obvious modes in there, like some of the
Yeah. Let's
grounding
see.
ones? I wasn't even sure what some of these are.
Yeah, so here's their kind of nice little diagram they have in the paper. that breaks down kind of all the vision tasks that they're doing. And what this graph shows is starting at the origin, you have the least amount of semantic understanding and the kind of lowest resolution image understanding, where when you move up semantic, you just get kind of base text labels, which is classification, just detecting the objects that are there, person, bike, car. And then you get to caption, where, it goes beyond and it gets more NLP like natural language sentence describing and something that's understandable what's going on. And then you get to fine grain semantic, so much more detailed, and you're actually beginning to map it to the bounding boxes inside the frame. So each one of these, to back up, each one of these subheadings is kind of one of those modes that's in the sequence to sequence tasks that this model's trained on. And then on the other axis, just focused sheerly on kind of spatial understanding, there's region proposal, which is just bounding boxes alone. So it'll throw a bounding box around everything that it detects. And then there's segmentation, of course. And then phrase segmentation.
I'm sorry, which of these run the fastest? Does like region proposal run faster than the object detection? Because I know with like OWL or some of the other ones, it actually like does the region proposal and then only outputs the ones to you that you like prompted it on, as opposed to like the reverse direction.
Yeah, from my experience, it's just a direct correlation with number of tokens that it has to output to give you the answer. So for me, you have several caption options. There's just caption, there is detailed caption, and then funny, they have more detailed caption. And so the caption alone, that's like a couple dozen tokens, so it comes out pretty quick. Same with region proposal. It's pretty quick at just throwing out all the kind of 4 coordinates that it needs for all the objects in frame. But yeah, my experience is I wish that I had the code up here and maybe had it running live, but unfortunately I'm not SSH'd into any of my machines right now.
It's okay. It is very promising. And I am hopeful that we could accelerate this, hopefully to 3x. It is interesting that at only 700 million parameters, it does only run at 1 FPS on a DGPU. So for the size model it is actually relatively compute intensive, right? So we'll dig in there. And my approach with the VITs, accelerating those, is to just use the torch to TRT library and basically hot patch the transformers code and replace the model instances with the torch to TRT one, and it will just like be able to reuse as much of the other code as possible, which that's what I do to support the different vision encoders used in the VLMs and VITs like CLIP and SIGLIP. And then for this VLA, I had to do a few others. So hopefully we can roll that approach. And I was just like browsing a few years ago, how did I accelerate BERT? And it looks like I was also able to do that with TensorRT as well. So these capabilities are very exciting and I think useful to people. So we'll dig into this and give it a try to see how fast that we can get it. And I know because you work on like IGX, and for everybody else, IGX is very similar to JETSON. It's just has a discrete GPU available in it, and that comes with the Hollow Scan SDK. And if Nigel, you very so kindly made a JETSON container for Hollow Scan that can be run on JETSON as well. So if you wanted to walk us through that SDK a little bit, because from just like browsing into it from looking at this code, it did seem like a really nice library to use. And I know that you've been working on it and have all your like demos in there and stuff.
Yeah, perfect segue. So just to throw the caveat out here, I did run this exact demo on just an AGX. We do support AGX. But there's a caveat with this demo where up here, this is a Qt UI. And for whatever reason, the Qt package was unhappy running on iGPU. So I was able to get kind of the app to run statically, where it's still the video feed, but just the like real time being able to change the prompt wasn't working, which is really annoying because that's the fun part.
Just pull in JETSON utils or whatever and do WebRTC and be done with it. And like I've never looked back after that. So we can combine forces and take the Agent Studio stuff and combine it with this, and because you have a bunch of really great reference apps and stuff in there.
Yep. So I'll get into it. So as Dusty mentioned, the other week we were able to get a Holoscan package into JETSON containers, and I'm really excited by this because my team has focused a lot on kind of traditional CV models, and we're great at that. But I really love the newer Gen AI stuff and a lot of all the cool things you see on JETSON containers. And we, as you can see, this is all the hardware that we support. And so it's essentially anything that you can run CUDA on, the Holoscan SDK supports. And so much of my time is spent compiling libraries that don't have wheels that I can just install. Like everyone just prioritizes x86. So I'm really excited to be on JETSON containers, have Holoscan in there, because now I can just let Dusty do all that.
We've always commiserated because you're one of the few other people that deal with the pain of being on ARM, and we should work more closely to make this work on eGPU also. And for everybody else's knowledge, there is a plan to like unify that driver architecture, so it will be easier in the future. Because I know now, Nigel, you do have some issues running with like, you can run MLC on the iGPU, but you can't get it compiling for the dGPU, and like your compatibility matrix is actually even more complex than ours because you want to support both. And like, wow, it's actually quite challenging.
Yeah. So I don't want to get too far. Paul, I've seen that you've had your hand up for a minute here. Did you have a question?
Hey, yeah, I just wanted to ask if you have any experience fine-tuning the Florence 2 large. I'm looking through it right now, and it does seem like there is an option to fine-tune it, like you say. I'm just more interested in how to get this up and running, so pass it on to my team in order to play around with it. So
yeah, unfortunately haven't gotten there yet. I just threw this out on HoloHub to get an inference app running because it's so much fun to tinker around with. But maybe in the next meeting, by then I'll have fine tune and I can talk more about that because I'm sure there'll be a lot of interest there.
Right. Yeah. And another interest I could see is I've used Cosmos from the Enterprise, the NVIDIA Enterprise models. I wonder when Florence 2 will be available on NVIDIA Enterprise. That's another interest I see.
Let me see if I can see internal traffic discussing that, because I know Cosmos was a foundational vision encoder, I think. But and I do know that when Florence 2 came out last week, the people were very interested in it. So I would not be surprised if there was an enterprise version of this or one that came. Well, you said this is MIT licensed, so it's already fine for commercial. But Paul, I put a link to the Hugging Face blog on fine tuning in there, and Michael alluded to a YouTube walkthrough video on it earlier. But if anybody goes and tries this, Nigel, Paul, or anybody in the next meeting or whenever, let's follow up and discuss those results. And I'll also take a crack at optimizing this and see how fast we can run it. Nigel, ideally in a way that like both of us can leverage you on IGX and also on JETSON and not use this wouldn't even be using MLC or AWQ or Auto GPTQ anyways. So we'll see what libraries there are in there. Hugging Face also has this Optimus library that back when Bert was coming out, that was how you deployed like optimized BERT models and sequence to sequence models. But since then, it's like everybody's moved on. So interestingly, now we're like looping back around to see that. But this definitely seems promising, and like people are interested in it. So we'll add it to the queue to get optimized and see how fast that it runs. It is interesting though that the OWL VIT and the others can be faster, and these do multiple modes. So if anybody does end up fine tuning it and like adding some new mode to it and can speak to how easy or difficult that is, I think that would be helpful to assess like what is this model essentially like a static set of capabilities that you can add new objects to, or could we like use this architecture to really build out whatever vision features you need for your application all in this like one little mini model? So including like the autonomous nav stuff that we were talking about previously. Okay, so that sounds like a good plan for investigating this and drilling down. And in the meantime, before the next meeting, if anybody does work on this and has some results they want to share, feel free to post it to the forums or whatnot, and we'll hop on there and discuss. Before I forget, Nigel, I know that we wanted to talk about grammars also.
Yeah,
that's something that you and I have chatted about for a while, and you have used those in your previous agents, and you commented here about like this being very good with JSON output, unlike decoder LLMs. And if you could walk us through like how you got into grammars, how you apply them to your agents, how you do it, that would be very useful info for us.
Yep, we'll get into it. So to close the loop on the SDK, just because I'm sure pretty much everyone here is probably unfamiliar, we are the team in NVIDIA that specializes in low latency, high throughput AI sensor processing pipelines. So a lot of our focus is with medical companies, where one of our partners is Moon Surgical here. Their Maestro system has one of these IGXs down embedded in the base of their system, and they run both the Holoscan SDK, which is our software, and the Holoscan hardware, which is the IGX. They have a A6000 in theirs, and they've completed a couple hundred surgeries now with that whole stack in Europe, which is wild.
That's great. Yeah. And when we first met, I know you were very focused on medical stuff. And I think even initially I was confused that like this was medical imaging, but now from browsing the repo more recently, I understand like it is a general sensor processing SDK, and that's very useful for us.
So as one of the examples of the non-medical stuff, one of the other fun groups that we work with is the SETI Institute, where for those not familiar, these are the people shooting radio waves out in space trying to talk to aliens. So we have a bunch of these IGXs deployed at the edge in the field doing signal intelligence on the edge before it's sent to their cluster for deeper processing. So we this kind of tagline of low latency, high throughput AI sensor processing, we thought that it was first a medical thing, but then very quickly got good at it and realized, all right, this is kind of everywhere. So
that is super cool, man. Yeah, I like it. And back before there was JETSON, like I worked with, it was these mil-spec DGPU systems that were used in like sensor processing and avionics and stuff like that. And then when JETSON came out, we kind of just trended towards the smaller end. But yes, sometimes I do daydream and salivate about the A6000 that you have in there. So
it's pretty sweet. The way that I put it is it's just a JETSON on steroids. We have 2 PCIe slots, a safety microcontroller, Mellanox ConnectX, BMC, all of these requirements so that we could work with medical companies, but it's proving to be pretty useful. But definitely they're a bit more expensive than an AGX.
It's awesome.
So there's that.
Is the A6000 a 48 gigabyte card?
Yes, it is. So
okay, so you can do a lot of fine tuning on that thing too.
Oh yeah, and I run Llama 70B quantized a good amount. That's a fun one to run.
Yeah. Nice. Well, how many tokens a second do you get out of that?
4-bit
like 5.
with 4-bit with TRT LLM. I think we get 20 something.
Awesome. Yeah. That's very usable.
Exactly, it's pretty usable.
Yeah.
So
And I think you have TRT-LLM because it's for DGPU, and for everybody else's knowledge,
Exactly.
like we are still working on TRT-LLM support for Jetson and have like a dedicated team now crunching on that, and hope that within, I don't know the exact timeline, but we'll make that available for production grade support of LLMs on Jetson. In the meantime, we continue supporting the different open source APIs and latest models, and then feed all that back through the Oregon software engineering teams.
Yep. So I'll breeze over this because I'm pretty long-winded here, but to just give a broad overview of what the Holoscan SDK is yes, it's for these sensor high throughput processing pipelines. And there's really two major components of that. And the main one is these operators, where it's essentially a component that takes in data, does some sort of computation, and then passes it along. And then the other component is the overall app itself, which defines all of the connections. So really very similar in a way to the agent studio that Dusty has been working on, at where it's just, it's pipe connections. You're taking things in, you're outputting them, and you're just connecting the pieces. Now, we don't have a nice UI, which after seeing what Dusty's been doing, pretty inspired. I would love to do something comfy UI like, because there's really no reason why we can't, because there's well-defined inputs, there's well-defined outputs.
Yes.
And
yeah.
so
I know. I was looking through your like plugin spec or whatnot, and think that I could just make a wrapper around it and like import it into Agent Studio that way. But I do wholly recommend that, like, you can just fork that web UI code, which basically I just pulled together from like popular open source JavaScript libraries. And I encourage everybody to go out and learn a little bit of like JavaScript and stuff. It's not nearly as gnarly as it used to be, and just do WebSockets or whatever is easiest. But in general, because now we have like Isaac Ross, Holoscan, Jetson Platform Services, all of the Jetson AI Lab stuff, and NIMS and Enterprise, not to mention all the other great open source SDKs. And if everybody has these connectors to other plugin APIs or nodes or whatnot, then I think that's an easy way for everybody to be interoperable and still maintain like the important features that they require, right?
Yeah, definitely. So I was going to show the video here. It's a little bit gory, but really this whole diagram is just kind of one of our meat and potatoes demos that takes in a video, converts it, runs it through one of our custom LSTM models, optimized with TensorRT, and then does some post-processing, etc. But we'll skip past that and get to something a little bit more interesting. So this is how we start to get into grammars, and how I got into grammars, and I'll explain what that is for those of you that don't know. But this was our demo that we had at GTC, right next to Dusty's booth at GTC.
Yeah,
and so
see, you already you got the web UI from the Llama sequence, so now you can just take the web UI from the Agent Studio too. Yeah,
exactly. So I was going to say, for those of you that are familiar with the Jetson Containers repo, you probably noticed this UI, and yes, it is the Llama Speak UI taken directly from the repo. So that was very, very helpful to get up and running. Now I'll play this, and
what is the Maestro system?
Can you guys hear?
What does it look like?
Yes.
Okay. So this is all on IGX running on A6000. There's several models.
Is a robotic surgical assistant that helps surgeons
switch to preoperative planning.
You have switched to episode 2, preoperative planning.
Pull up the preoperative image.
Turning the rendering tool on.
Spin the rendering to the left.
Nice. So it's doing tool calling, function calling, or is it just constrained JSON that you made it to?
Constrained JSON. So yeah, this was my intro to grammars, where I'm sure that you guys notice this is kind of some funky output here. This is some not your usual just text only response, and it's pretty custom. And getting ahead of myself. None of that was fine-tuned. That was all.
Wow.
This is just a for the vision language model. We fine-tune our own vision language model that was fine-tuned for understanding surgical scenes. And then the LLM that we have running both on the IGX locally was just the open chat model, which is, I think, a fine-tuned Mistral,
Okay.
both quantized.
Is this open chat that you're talking to, or is this the VLM?
It depends on which thing you're using. I think pretty much everything I showed in that video was all open chat because
Okay.
none of it was
Okay.
visual understanding.
Okay.
And yeah, so let's get
That makes
into
sense because like I can't get the VLMs to like chat or do
no.
anything other than what they're fine-tuned because they fine-tune them really hard.
Exactly.
Yeah.
So the way that all of that was working and was when one of our holoscan operators that we made, but it's really a wrapper for our agent framework, where for any query coming in, we would have ASR, just Revo running, and that text was sent into a selector agent. And the reason for that is we had all of these different agents and tools, and initially what we had was just a giant monolithic prompt defining each one of those tools and the parameters that we needed. And maybe something like Claude with a big context window can handle that sort of complexity and could output the right parameters. But what we found is just it was overwhelming our poor little 7B that was quantized. And so we had this selector agent that was given just kind of general descriptions of each one of our agents. So we generalized and just made a visualization agent, an annotation agent, and so on. And then so we given the input text and kind of the message history, and then decided which agent to use. And then the agent was given that input and then had the fine-grained tool definitions and could output the relevant parameters. So each one of those.
I'm sorry, is the selector like a classification model or is it just some other heuristic that then routes it to?
It's an LLM that was using grammar, which I apologize, I keep alluding to, and I'll explain more. But essentially, this model is outputting a JSON spec where it's always going to be a string that is either visualization agent, annotation agent, chat agent, so on. So the grammar is the beautiful thing I was going to explain, that each one of these little boxes, including the selector agent, is made up of our base agent class, where it describes which model it's using, whether that's our LLM or our vision language model. That is a prompt, of course, everyone's familiar with. But then the key thing is the grammar. The grammar is what allowed us to do this and have all these complex calls. So keep preluding to grammars, but just for a quick recap so I can build up to the grammar. Recap on how LLMs work. This is an absolute simplification, but at a very high level, you have an input, turn on the lights, and then at a given point in the generation, you will have some output. So in this case, we have sure, I will turn on. And again, the simplification here is that the output tokens are just full words. We're not doing byte pair encoding or anything here. It's just simpler to conceptualize. So then your output is really logits / probabilities for your entire vocabulary. And you apply softmax to that, and then you take the next most likely word, which is in this case the. So the output becomes sure, I will turn on the. And this can be any LLM. I just use Llama, but it can be Mistral, anything you have access to. Now, the way that grammars work and the way that whole demo works is same input, output works in a similar manner. It's a little different here, but we'll explain why. So the model still will output its logits / probabilities for the entirety of its vocab. But then instead of just being directly mapped to its output vocab, you have a logits processor, which when you use a grammar, ensures that what is being generated adheres to your grammar. So my team in that demo uses Llama C++ and their grammar constraints. And the way that you define a grammar with that is use a Backus-Naur form grammar, BNF grammar. And the way that it kind of works out is you have variables where a key here we define as the string lights, music, or alarm. And then the variable value is paired to either true or false. And then the root variable is in BNF, kind of your meta overall grammar that kind of puts everything together. So here you have a opening bracket, one of our keys, followed by a semicolon with a space, and then followed by our value with a closing bracket. And so what the logic processor does is when the LLM is generating, before it applies kind of maps to the final output vocabulary, it modifies all of the logits / probabilities, and everything that doesn't meet your grammar, it sends to 0. So the model can't actually output that token. So you see here, going into it, the was going to be the next token, but because that doesn't meet our spec that we've defined, it's sent to 0, and the only thing left that meets our grammar is this closing bracket. So then we get valid JSON output for lights equals true. And just another visual I have here is from the paper Grammar Constrained Decoding for Structured NLP Tasks Without Fine-Tuning. And I thought this is just another nice visual to kind of see how generation works, where really the way that these logic processors work is they build a computational map where they build a map as the model's generating of the possible paths through the decoding phase. So I will pause here if there's any conceptual questions.
It does make a lot of sense. And it's just in the Transformers API, there's these like logic processors and such. There's just like it evaluates the grammar. It can be a BNF or the pedantic ones.
Yeah, exactly.
Or like pedantic. The tool calling, I've seen those, and it would like llama.c++ uses these BNF, which like gives me flashbacks from undergrad, like the Noam Chomsky grammars. I'm like, oh man, I don't necessarily want to have to like author those, which I'm presuming that you went in and did for your more complex scenarios and debugged all that. Yeah. Yep. On the tool calling side with like, so how it automatically generates the tool descriptions from your Python functions is it just uses inspection and then makes this like OpenAI compliant like JSON for it. But then there's a pedantic library that will put it into like this grammar, form of a grammar that it was then trained on and then does it. So it's interesting, like compare and contrast here that some of these tool calling models really it's doing the same thing. It's just those were tuned for it and don't need an external grammar logics processor after, which in my experience, any of those samplers or things that touch the logics do significantly impact inferencing performance. Yeah. But at the same time, while these tool calling models are quite reliable in adhering to the JSON schema, they do mix up the functions themselves now and then. They're like tuned for it. Whereas like you can make this work for other things and have different JSON schemas there. And it would seem since you're using Llama C++, you're using the BNFs. Can you speak to if you're just using general inferencing or like wanting to add this into others, like all the other inferencing APIs, what approach you might take to support that?
Yeah, so I'll get into it with some pros and cons that I put here for function calling versus grammars. But to answer that question immediately, that's kind of one of the downsides I have here is that for inference engines, there's really limited support and it's hard to find right now. So there's Llama C++ that does it like natively built into the inference library itself. But then also there's projects like LMFE, Language Model Format Enforcer, which acts as kind of a wrapper to other inference libraries like VLM and also TRT LLM. So they have tutorials in there on how to do that for both of them. So yeah, that's kind of one of the cons, but I'll jump into it. So function calling, and again, this is anecdotal. This is my opinion. This is not factual by any means, but I think it's a good discussion to have, especially because I think that between function calling and grammars, this is kind of what takes LLM usage to the next level where, chatbots are cool. Chatbots are fun. But when you start to actually have your LLM execute programs, that's when things get interesting, in my opinion. And function calling and grammars are the ways to that. So function calling, pro is that they are supported by many inference engines. It's not really hard to find an inference engine that runs locally or even any of the APIs now. Like OpenAI does it. I'm sure Claude does it. Mistral, they all support function calling. Now also low latency, what Dusty touched on there is because you're not touching the logits, it's just normal generation. So whether you're just chatting with the model or doing function calling, it's going to output at the same speed. And then this final pro, I go back and forth on this. I'd say it's easier just because it's more constrained. You know, it's the OpenAI API spec, and it's just very well defined and constrained on what is what. So it's, in my opinion, kind of easier to make less errors just because it's so narrow and constrained. Now, one of the cons is that you need a specific model to do function calling. You can't just throw in Llama 3 8B and tell it to call your function. You need something that's fine-tuned to do that. So as soon as a new fun model comes out, you can't, unless it supports function calling, you can't just throw it in your pipeline and have it use your tools. You can only use a specific subset. Another con that I had is the rigid tool spec. For me, some of the use cases that I had, it seemed kind of unintuitive to make it into a function call. You know, if I just wanted a simple Boolean, it seemed like a lot to define this whole function spec to just get something to be on or off.
It's very verbose. And I would say that's like one of the biggest cons is you put in 5 tools and now your system prompt can easily be like 1,000 tokens.
Exactly.
And it's actually an issue. And I'll show with the Llama factor here that can do as a function calling data set built in. And it occurred to me like, if we can fine tune it, then we could change this pedantic spec to be much more compressed and not so verbose. But I'm neither here nor there at this point. And it does occur to me like the one actual difference with function calling is not only you actually like invoking Python code, but then there's that return response into the chat typically that then you want the bot to then like respond to and potentially recursively make more function calls and that like agentic thing where it's like processing and like doing the stuff, as opposed to the grammars. It's really for enforcing like the data output that you want from it, and it's not necessarily tuned for multi-turn recursion and whatnot.
Exactly. Chugging along, the final con for me, that the reason why I haven't used function calling a lot is just while you can have capable models that are good at function calling, at the end of the day, because the generation is no different than normal, chatting, there's still going to be hallucinations. It might output the right function where you have 2 input parameters defined, and it might use 3, it might use 1, it might use the wrong type. So that's kind of the con for me. Now, going to grammars, the number one pro for me and why I like them is that it will always follow your provided grammar. There's an asterisk there because, if you output a grammar that isn't in your model's tokenizer, it's not going to work. But, if you give it something like this, you can always count on that being valid JSON and it adhering to whatever you give it. And that goes into another pro, which is reduced post-processing. Because it's always going to give you whatever spec you give it, you don't have to have all this error handling, check that it gave you the right number of parameters, check that it gave you the right type. You can kind of just know that it's going to be a Boolean value if that's what you want. It also works with any model, so you can throw in anything that you have access to the logits. You can throw in Llama 3 8B, it works. You can throw in a small language model, it works, and so on. And then also just the flexibility of the, essentially what it is regex. So whether you're using Pydantic or BNF, it's really just regex. You can define it to be anything. And while it gets a little bit complex, ChatGPT is always your friend. So give it one example and then tell it what you want it to do. And it usually does it pretty well. Now, biggest con is limited support. Llama CPP is not the most optimized inference engine, but I'm kind of married to it right now because of the grammar constraint that it supports. Also, there's the false confidence issue, where this is an extreme example, but you can take a language model with randomly initialized weights and create a beautiful protein structure grammar, and then run inference, and you'll get valid protein structures coming out of your model. It doesn't mean your model has any idea what it's doing. It's just being constrained to the grammar. So kind of best practice here that I've noticed is in your prompt, you kind of want to use it like function calling. You're going to give an example of what spec you want the model to output, and you kind of want the model to be prompted so well that it's going to output to your spec even without the BNF grammar enforcer. And it's really just there as like a guardrail where, one of the tendencies of LLMs that's very annoying is if you ask it to output JSON, it'll say, sure, let me give you the valid JSON, and then give you JSON. So the grammar spec is great because just first token, it's a bracket. So that's kind of the way that you want to use this is don't just throw in a grammar and give the model no idea that you're expecting a certain output. Like always condition it and almost pretend like you don't have that grammar enforcer there. And then the other con, which Jesse alluded to, is the performance impact. From my experience with the Llama CPP grammar, you can expect like a 15 to 20% hit. So again, anecdotally, if I have a model that'll
that
run
much, really?
yeah, so well, generally, let's see, maybe my math is off here, but if I have a model that's running at like 50 tokens per second, it may run at 40, 39, something around there.
Okay. Yeah. And
But-
Llama C++ is pretty optimized on the CPU side
Mhm.
for things. And like it supports CUDA but doesn't have all the CUDA bells and whistles. I was just Googling in the background. I previously looked at this. It was like a summary of different agent frameworks and the different methods they use for like constrained JSON, token healing, grammars, or like different approaches that folks are using for it. I think I previously sent you that somebody did this Torch Grammars port, which was to like try to replicate what Llama C++ was doing in the likes of Ooga Booga and other, but this seems like abandoned and I never really got into it. This was the only one I could find that did eBNF, but there are other, it might be possible to integrate the pedantic, or other libraries like this into it. And I would think at some point TRT-LLM would have like a CUDA version of this even and be super fast.
That's what I really want to see. I just sent a link to LMFE. I haven't used it a lot, but in the samples, they do have a TRT LLM integration and how to do that, where this library really works like a wrapper. So TRT LLM, like within a couple months ago, they had a update where they exposed the logits, so you can do whatever you want with them, and that's how this LMFE takes advantage of that.
Oh,
And
nice.
I have not ran this. I don't know about the performance impact.
Okay.
Yeah, I need to dive deeper into the implementation of these grammars and how they actually do this. But
yeah, like
I believe that
like people commenting on Reddit were like, "This is like slow," and I don't mean this one that you linked to, but this does look interesting because it looks like it uses pedantic too, which is could be. And again, I don't want to be married to any individual one, but that one is kind of interesting. And like, you can just give it a dictionary of like, this is what I want, and it will output the pedantic, and like it can translate it from there. I will add this to the list to look at as well. This could be promising way to, if it can just operate on logits, then that's really all you need. Okay.
Yeah, that's all I really had. So please check out the new Holoscan package on Jetson containers, and also the SDK and HoloHub, which is where we have a bunch of examples of Holoscan SDK apps. All of it's open source. You can tinker around there as much as you want.
Yeah. No, thank you so much, Nigel. This was very useful, even like for me. I've been wondering about all this stuff, and it's been great collaborating with you. And also like Sammy from the JETSON Platform Services team, and you guys have been great to work with and like bounce ideas off, just like we do in this community group. So we'll work together to, carve out different things that we're focusing on, and ideally, down the road, be able to merge our efforts and take the best of what everybody is doing. Because even so, we've basically been like full bore on this now for like a year, getting Gen AI running at the edge and everything. And but now it's coming to the point where like the stack is maturing and we got all this stuff going. So being able to combine the best of everybody's going forward will be great. So this whole discussion of the grammars and the fine tuning is like a segue into our last topic, which we'll keep real quick, I promise. And I'm not sure if Elaine from Seed Studio is still on, but they had graciously made a container for Llama Factory, which builds on the tutorial that Shagazat did and we discussed last time. But Llama Factory is just like a nice web UI built around all these like fine-tuning scripts and stuff. Think of it kind of like Ooga Booga or TextGen Web UI, but for fine-tuning. And in general, the issue with like fine-tuning is you got to dig into the specific model and follow their data set format and like learn it all. But in this one, it just is a Gradio Web UI. It supports like a lot of different models, not all of them, but I believe you can put in custom ones from Hugging Face, and any Hugging Face model that supports LoRa's or whatnot can work through this tool. And there's different, you can do full fine tuning, you can freeze layers or do a LoRa. I did try to do the full fine tuning a bunch of times last night and it froze like every time, even on JAL 64 gig and using like 5.3 instead. So I'm not sure that full on fine tuning is in the cards for us, but the good news is the LoRa works great. And it's been running in the background here before the meeting started. I started running it on this function tool calling data set, which it's also preloaded with all these data sets here, like Alpaca or this Glaive tool calling one. It's like one of the most popular tool calling ones out there. And you can add your own data sets as well to this. This is what the tool calling one looks like. I haven't really gotten into it, but this is what I was mentioning, like, oh, we could just change the spec of like the data set if we're able to do this. So you basically just set up all these options. You can go into here and select like 8-bit or 4-bit quantization if you need that for running it on like ORAN NX or whatnot. I've just been doing it purely in FP16. There's a bunch of other stuff here that you can set to for the LoRa's. I just have left it on the default layers to process with the LoRa's. I would like to be able to like extend this further because it does print out like the number of trainable parameters that it's able to use here. Like right here, I'm only training on 0.26% of all trainable parameters right now, and the memory usage is at 25 gigabytes. So it's pretty low. I'm trying to find a medium in between the LoRa and the full-on fine-tune, which like keeps blowing up completely. In my experience, it runs at like 1 training sample per second. So it's not setting any speed records here. In the previous test I was doing, it was mainly just on this like Alpaca fine tune for 1 epoch, and it takes like 45 minutes or something. So it's like within the realm of possibility. And really all this does is this wrapper is just this web UI is a glorified wrapper for a command line tool that it generates the command line for. And I was trying to show the thing here, but it's actually running in the background. Let me see if that's still going or not. Yeah, it's still going. But you can see with these config files that you can also give to it these settings are all in there, and then it makes this like torch command line that will then go and run, and it just like logs all of this. So my point being with that is we could actually integrate this or other tools like it into our more like runtime components that already have the sensor data, like HoloScan and Agent Studio and all of that stuff. So like, let's start logging our chats and interactions and collecting all the video streams for the VLM and stuff. And when you hit some like critical mass of chats you've collected, whether that's tokens or episodes or whatnot, then it'll just like issue this command to kick off the job, and it might have to like pause the robot or whatnot. Ideally, your data sets will be smaller, so this could hopefully take only like a few minutes to update the LoRa or whatnot, and just make this whole like interactive workflow much more easy and streamlined. So you're not always like, okay, I'm gonna like log some data and then go in and add to your data set and like start up the job and test the model. And if it's all just much more iterative and quick, then that can be very helpful and I'm more so thinking for like the on robot deployment, kind of like JetBot was, where you just like drive it around and then train it for like a few minutes in PyTorch on Nano, and then it can go off and do road following, and you can just iteratively do that until it gets better and better, as opposed to like just doing this for chatting and chat personalities and stuff. But there's a lot of different examples in here. It does appear that it can do multi-node as well. I know it does multi-GPU. I'm just kind of interested in that because like I do have a bunch of JETSONs here sitting around that just like build containers and stuff. Question from the group, please go ahead.
Yeah,
There's
hello.
any. Hello.
Am I
Hi.
audible?
Yes, we can hear you.
Yeah, hi. So I had a question regarding VLA, the Open VLA.
Sure. Yes.
Yeah, so the data set we are collecting over there, we are dividing the range into 256 tokens, right?
Yes. Yeah.
So how is that range defined? As in, how are these tokens defined over there in the action
Yeah.
space?
That's a great question. Okay, because I was digging into this and then trying to like characterize how they did this, because I do see it as an issue that it's only 8-bit resolution, right? So what it says here is that because they want to retain the natural language capabilities so you can talk to it while outputting the values as tokens. It does not print out like 0.1256 as text. It just outputs a token that represents that value. And since Llama 2 only reserves 100 special tokens in the tokenizer, they're like, that's not enough, we can't use that. So then what they did was they found the 256 least used tokens in the vocab and overwrote those in the training. And Llama 3, the tokenizer is much bigger, but it still only has 256 special tokens available. So I'm just like chatting with like our research teams about this and stuff. I was discussing with them that like, if you retrain one of these from scratch, like let's say you do a new foundational model, an SLM for this or whatnot, that's not Llama based, or like you're going through that trouble, put a lot of extra tokens in the tokenizer to support this. And then you'll be able to do, I would think 10-bit, 1024 values possible for token, or 12-bit for 4096 would be acceptable. Walter and the other Ross guys, I don't know if you have any feedback on that for like PWM control and stuff. I know like 10-bit is generally regarded as being kind of necessary for it. Here's the code modifications that I had needed to make to support the VLA on top of the VLM pipeline. And it is just like the same. And this is all in the NanoLM code already. You can go out there and get it. But this is the part of the code where it actually does the decoding. And you can see here it like rescales from the bin back to the original -1 to 1, and then it denormalizes that to a value that's been calibrated for like what the range of the arm actually does. So there's like multiple layers here that it does, and there's a lot of things that they're all still learning about this and whatnot to characterize, and that's one thing that we're really interested to get started on this and learn too about like how to apply it, what can be improved, and where do we go from here with it. But yes, that's the deal with that. Why there's only 256, but at least those are independent of the actual tokens. So it outputs 7 tokens. Generally, those are mapped to like the gripper state. Then there's a 3D world coordinate pose, and then like a 3D rotation. So that's where it gets the 7 from. And each of those 7 is represented by one of these 256 token IDs. But fortunately, like each token is independent, so they like share those IDs, and the model learns that like, oh, I'm on token 2. That is like the world X position that it needs to do. So it is pretty smart in that respect. Any other questions at this point? We're running a bit over time, so with that, we'll try to wrap it up soon here. Any other questions from the group?
Actually, just a follow-up question to this.
Sure, yeah.
Yeah, so if I were to create a data set of mine using different hardware, so since we are using 7DOX robot over here, so I have a different robot morphology on which I want to create a data set. So
Okay.
I'll have to like define these 256 tokens as per my range, and then
No,
like
I don't think
move
you don't
as
need to change
yeah.
that, because there's no changing that unless you completely redo the like llama from scratch, essentially. Because if you change that tokenizer, you got to go back and do pre-training on it, right? As opposed to their LoRa scripts that they have here for it, where like you're just sticking with it. So you don't have to worry about mapping the bins. But what you can do is there, just real quick, I'll show you where the configs are in. Okay, so the normalization stats. This maps, so first it takes the token IDs. Those can be in range of 0 to 32,000. Most of those 32,000 are for text. Only 256 correlate to actual control outputs. Then it rescales those from -1 to 1. Then applies these normalization stats that are specific to each data set or robot arm setup that you have. And these Q values represent like the 1% and 99% range of whatever joint that you're working on. So you basically like define these for your robot, and then it can then scale it and is adapted through fine tuning. But if you're working on this and want to collaborate, I would love to do that. Please reach out after the meeting, and I'm happy to chat more with you about it.
Yeah, definitely. So where can I contact you on this? I'm actually working.
Yeah, you can find dustinf@nvidia.com is my email, or on the forums, or here, I'll just put it in the chat. And it would be good to do on the forum so we can all follow this topic. I'll make a thing about this on the JETSON projects, as we've done in the past with like the Home Assistant stuff, and when that was really spinning up. But we can do that and work on similar wavelengths with where we're heading on this. But if you are interested in fine tuning this for your specific robot and want to prove out that workflow. That's like exactly what the steps that we're trying to go through now, and would be very valuable to collaborate with others on that. So that's really cool. You're interested in doing that too. Okay, so with that, thank you so much, Nigel, for that very educational overview, and love to have you back next demo or app that you come out with, and we'll look at the parameters. And actually this Florence too will jump like up to the top of my priority list. But if there are no other questions for today, we'll close the meeting with that. Again, always excited around here, and these vision models are super cool, and I can just see like months of work ahead to prove all of this out. But I'll let you guys go. Thank you so much for sticking around. The meetings are always great, and is very educational for everybody involved. So thank you guys so much. The next meeting will be in 2 weeks on July 30th or July 23rd. Okay, and we will keep working on this stuff until then. All right, thank you guys so much. Have a great afternoon. Appreciate you all as always. Take care.
Thank you. Wish you a good day. Bye.
Bye.